SwayamPrabha. Digital India. Educated India.
Welcome to lecture 2 of week 6 on the NPTEL course on Muffler Acoustics. In this lecture, today's lecture, we are just going to pick up the things that we left in the last class. It is just going to be, today's lecture is just going to be about combining the momentum and continuity equations along with the isentropicity equation to arrive at the final form of equation, where the variable to be solved, field variable, is the acoustic pressure. We will end up with the Webster's horn equation. We will look at the different rather simple algebraic steps now to how to arrive at the equation, and then we will look at the different cases. Well, perhaps only mention it and take up the cases, possibly one of the cases is analyzed, and then rest of the cases can be analyzed in the next lecture, lecture 3. So, let us begin quickly on the process of linearization and combination of Euler equations and the continuity equations. Okay. So, now this was our today's lecture, lecture 2, but before that this was something that we must have a look at, rho times del del t of u plus del del x of p. This is one thing. Momentum equation the same as that for the uniform duct, but the continuity equation was a bit different. So, this was the one, but we could possibly write it in a more simple manner, which is the one that is highlighted in red color, del del t of rho plus rho u times del del x of log x plus del del x of rho u. So, let us see how we combine these equations. Let us first cleanly write it down again somewhere here, del del t of rho times rho u into natural logarithm of the area plus rho u x is equal to 0, and the momentum equation that we should be worrying about is rho naught times this thing p tilde times x, and this is actually linearized. So, I would call this is rho naught u tilde, and this is of course after linearization and dropping of the second order terms, as we discussed in the beginning of the of this course. So, we get this thing. Now, this is equation, let us say 1, equation 2. Note that equation 1 that I have written here is a bit different to what was written in the last class, because obviously there was term like rho times u. Linearization was not done until that stage, and it is only here that we assume rho is equal to rho naught plus rho tilde, and u is equal to capital U naught plus u tilde, but u naught is 0. So, u becomes simply u tilde and rho is equal to rho naught plus rho tilde. It is basically the same thing that we have been talking about so far in this course, linearization. U is equal to u naught plus u tilde. This is what we get, of course, and in addition, of course, P the total pressure P is equal to P naught plus P tilde. So, this is what we get. Now, once we substitute this thing and this thing as well as this one in the, probably not this one, just these two equations in the continuity equation and drop the second order term. So, based on a non-dimensionalization arguments that we presented in the week 1 lecture, that rho tilde into u tilde is a second order term, or rho tilde times u tilde x is also a second order term regardless of the derivative, and all those all those arguments, we can figure out that rho tilde times any quantity that is a product of these tilde terms regardless of the derivative being there or not, is a second order term. When we invoke such arguments, we can figure out that these are second order terms, can be safely ignored in the derivation, and finally we will end up with the linearized form. And Definitely now another thing that comes to our notice is the isentropicity holds, that is the entropy change is 0. So, but P tilde is equal to C naught square times rho tilde, that is small changes in the acoustic pressure is equal to small changes in the density times square of the sound speed or the disturbance of the propagation pulse, where C naught square is gamma times P naught by rho naught, where P naught is the atmospheric pressure and rho naught is the ambient density. So, this is small signal wave equation which we are considering. Let me call this is equation 3. So, when you put this equation in equation 1, as usual, what do we get? We get it is 1 by C naught square times P tilde by P t plus rho naught times u times log S x plus rho naught times u tilde x, okay, is equal to 0. We also have our this equation. So, as usual, if we differentiate equation 2, that is this equation with respect to x, and differentiate this equation with respect to t time. So, what do we get? We get this square plus rho naught times, remember now this cannot be a function of time. So, this is just this part and rho naught times u tilde x comma t. So, I probably can write it as u tilde comma and p tilde x x, that means twice partially differentiating with respect to the pressure. So, we get this and we get, well, equation 2, what do? We do rho naught times u tilde x t plus p tilde x x, isn't it, is equal to 0. Okay. We put this equation in here. So, what do we get? We get I am so sorry, this becomes my mistake, this becomes T t, because remember we differentiate with respect to t. So, that was my mistake, sorry. So, T t plus rho naught times log S x plus into u tilde t minus p tilde x x is equal to 0. Okay. So, we get this thing, but then we still have this guy sitting here. So, what do we do with this guy? We again probably resort back to your rho naught times, you know, let us have a look at this thing. Obviously, in a compact manner it can be written something like this. So, this can be simply put as minus p tilde x. So, we can definitely do that. So, once we do it, we get and transpose all the terms on the right hand side. So, we do the transposition of these terms plus the substitution of u tilde is equal to minus p x. So, once we do that, we get p tilde x times log S x into rho naught. So, you get rho naught here is equal to 1 by C naught square times p tilde tilde. So, your these two terms get cancelled and you are left with T t is equal to 0. So, finally, well, we arrived at the wave equation, Webster's horn equation, which obviously is the same as this one. So, we get this form. So, that was the equation that we talked about at the beginning of lecture 1. So, we are there with a little bit of rigorous derivation. Some terms obviously I would leave it to you guys to simplify and kind of work out term by term, but as usual, as a check of self consistency, it is valid for a plane wave propagation in a uniform duct as well if you set Sx to be constant. So, this term would then go away. In general case it would not. So, we let it be, and now to derive the Helmholtz equation form for a horn. So, basically what we do now, insist time harmonicity. So, that is to say we assume E j omega t. So, once we substitute this guy in the equation, let us say equation 4 or the much sought after equation. So, remember P tilde is nothing but j omega p x, and this thing would become minus omega square times p x, isn't it, j omega whole square. So, we get this, we substitute back in this equation. So, and realize that omega by c naught is equal to k naught, right, the wave number with units per meter is angular frequency by sound speed. Once we substitute that here, so what do we get? We get ordinary differential equation form So, this then is the Helmholtz equation for the duct with a gradually varying area, and this we can solve for a specialized cases. So, now the salient thing to be noted from the equation here, the star marked equation here, is that unless Sx is known, we probably cannot solve it. We need to know the form of Sx. So, if obviously the trivial case is Sx being a constant cross sectional area, so I will probably not discuss that from now on. This in this equation, the coefficient of this particular guy is 1, and this is k naught square, which is well constant at least with respect to the space x. But what is not constant is this guy. So, if this particular thing is constant, so we get a equation with a constant second order differential equation with a constant coefficients, and we can happily solve it by substituting or assuming e to the power some exponential function and solving for the value of the exponential. So, all these things we can do, which would lead us to the fact that we will be getting equation whose analytical solution is known. Let us work out a few cases. 1 by dds of this thing, if this is constant and let us say this is alpha. So, what do we get? We get we can actually integrate it, take the limit and sort of integrate it and get alpha x. Do not worry about the arbitrary constant of integration, or probably we can, it will come out e to the power alpha x into e to the power c, let us call this another b, is equal to s x. Now, what does it mean? At x is equal to 0, let us say S x is equal to S naught. So, B becomes S naught. So, S x becomes S naught into e to the power alpha x. Okay. That means what does it mean? If you start somewhere here, you will gradually be going like this. Let us say this is your axis, radius would increase. So, you will get a duct whose cross section gradually increases. Okay. So, such a kind of a duct whose cross section increases in an exponential manner, or radius also, because remember obviously from our elementary knowledge S x is nothing but pi into r x square. So, your r x, r as a function of x, would become S naught by pi into e to the power, you need to take a square root of this, and this would become alpha by 2 into x. isn't it? So, it is just another constant. Basically the idea is that duct whose radius is gradually increasing exponentially does have an analytical solution for acoustic one dimensional acoustic wave propagation, and let us see what we get. So, we assume that we are getting this alpha here. So, we will substitute alpha in here. So, to arrive at the following form, which is your alpha times this thing plus k naught square times p tilde. So, this is equal to 0. So, now any guesses how do we go about solving for it? Is there any guess? Note that p is nothing but 8 e to the power j omega t, which we already assumed the moment we considered a Helmholtz equation kind of a solution, j omega, remember, but that is what we did here, e j omega t. So, it is p x, so it was p x, but now we are assuming it to be having this form where a can also be a function of x, and we need to find out a, or you know, some a can be which is a function of x, we can need to find out this thing or the solution of this equation. So, how do we go about doing that? We can assume a as a function of x or possibly some other thing. Let us consider p tilde to be, let us say it has a as a constant or e minus j k x into e to the power j omega t. We need to find for k. Now, k is different from k naught, that is k is not equal to k naught. K naught, remember, it is omega by c, k is some other exponential constant. So, obviously, when you substitute this guy here, and actually we can sort of neglect this part because time is already taken care of. So, let us say a is a constant, a is a constant here, it comes, it will be taken out everywhere. So, I will not bother writing it. So, minus j k, that will become minus k square plus alpha times minus j k plus k naught square is equal to 0. So, once you simplify the above equation, you will get j times alpha k minus k naught square equals 0. So, k becomes minus j alpha plus minus root over j alpha whole square plus 4 k naught square by 2. So, j square becomes minus, so minus alpha square plus 4 k naught square by 2. So, this becomes minus j alpha by 2 plus minus k naught square minus alpha square by 4. So, we get this particular form, and we can actually simplify this thing further. We should, in fact, k is equal to plus minus k naught times 1 minus alpha by 2 k naught square minus j alpha by 2, isn't it? We get the following thing. Okay. So, what does it mean physically? So, now clearly when alpha is 0, that is your flare angle is 0. So, remember, recall the relation, when alpha is 0 is a constant cross section area duct. So, when then in such a case k would become plus minus k naught. So, that is a normal duct of a uniform cross section area, but obviously we are interested in the non-trivial or the more interesting case of an exponential horn or an exponential duct. So, this would basically mean that the wave number is deciding whether the wave would be propagating or not. Now, clearly we assumed a solution of the form a into e to the power minus j k x. So, already j is there. So, k has to be real, k has to be real. Why? For propagation. If it is not real, then what will happen? J into j, that is your exponential will have a decaying term. Obviously, exponential, the solutions cannot grow exponentially, so that term has to be suppressed, otherwise we will be violating the linearized wave propagation theory. So, the signals will exponentially decay, that is still a physical solution, but then that would mean evanescent modes. So, remember the discussion in week 2 of our course, there are two kind of waves, the one that propagates or normally has a sinusoidal or some kind of a wave pattern. It may have a decaying amplitude with space, or it may not decay, it can just propagate unattenuated, but at least it is propagating. Other kind of wave was evanescent wave. So, it does not propagate, just decay. So, if you have a space coordinate like this, and you can have a solution like this, or you may have a solution like decaying wave, but then there are solutions which do not propagate at all, which just simply decay. So, we are interested in this guy, talking about this guy here. So, such a thing is called evanescent waves, or at least that waves which decays much faster in comparison to the other dominant term, they do not propagate at all. So, why am I telling you about all this thing now? Because you see here that this particular term, if the term inside the bracket, that is this guy, if this guy is greater than 0, then obviously there is no problem, and there will be some kind of a, along with the propagation thing, there will be some kind of a spatial decay as well, because j gets multiplied, and you will have you remember the solution was minus j. So, minus j, so minus plus j square is minus. So, minus alpha by 2 e to the power, you will get some part will be e to the power minus alpha by 2, alpha being constant, it will signify a decaying part along with the propagating part. So, you will get something like the green kind of a solution spatially for a given frequency, k naught is the frequency. So, for a given frequency, if the value encircled here, if this is greater than 0, then it propagates, no problems, but if it is not greater than 0, if it is equal to 0, still you will get some decaying solution, the wave will be just about to be propagated, or it is just called a cut-on frequency for the wave. Remember the cut-on frequency concepts that we talked about in the week 2 lectures. So, same thing applies here, but in a different context. So, for an exponential duct, for an exponential shaped horn, cut on frequency is 1 minus alpha 2 k naught square should be greater than equal to 0. If it is less, then it is evanescent. So, the idea is that 4 k naught square minus alpha square naught greater than 0, it would basically signify that alpha by 2 pi f by c naught greater than alpha by 2. So, f should be greater than c naught by 2 pi times root over alpha by 2. So, if the frequency of excitation is greater than this number, then of course, the waves will be cut on, that is they will propagate. If it is less or at least equal to, then it will not be propagating, they will be, it will decay down exponentially. So, that is an important thing. We never actually encountered such a thing for a planar wave propagation in a duct of a uniform cross section area. So, no matter what frequency you are assuming, if it is if you are considering planar waves, they will always propagate, right. But for a thing like an exponential horn, we could get a clean relation between for the cut on frequency, let us say, let me call this f c. So, you need to excite, if you know alpha value is typically a bit small value. So, beyond a certain frequency, almost all frequencies would sort of propagate, alpha is a constant. So, below that the waves will not propagate. So, that is something new what we are kind of seeing in this kind of a thing. So, and then of course, then there are things like amplitude decay and the phase velocity relationships for the exponential things horn. So, amplitude decay is nothing but we saw basically this part is there e to the power minus alpha. So, if we assume the amplitude to be A, so it is basically amplitude decay would basically mean it is something like this, and e to the power j times whatever part into e to the power j omega t, something like this. So, this is the Ax function that I was talking about. It means a decaying function, amplitude decay with respect to the space x. Now, similarly, you can derive phase relationship between velocity and the phase difference between the velocity in the pressure and the phase velocity. All those things we can easily do, and we can get an amplitude of the RMS acoustic pressure field. We can show that it is decaying approximately, for an exponential horn it is decaying as 1 by root s, and we can do all these kind of detailed derivations, but we will probably stop here, and in the next class what we will do is we will consider the case of a conical muffler or a conical duct. We will derive the acoustic pressure field solution and the velocity field solution. We will focus a lot on conical shaped ducts because they are used in resonators called CCTRs, conical concentric tube resonators. We will analyze that in probably in week 7, towards the end of week 7 or probably towards week 8 beginning. They are used a lot in these two wheelers, the photograph that I have shown you. The internal section comprises of uniform duct with the perforations, and the annular cavity is a conical annular cavity. So, there are lots of things that we could do, and SX being general, we can keep studying. I will probably mention some of the important things like parabolic shaped ducts, hyperbolic shaped ducts, the solutions which were known since a long time. It's now, there have been papers published on that which report exact analytical solutions, but SX in general is not, for general SX the solutions are not quite known. There are a lot of approximate methods like WKB method and all those kind of things. So, what I will do, I will kind of introduce the conical shaped horns or mufflers in the next class, and then mention some of the cases which have an analytical solutions, and some approximate techniques, analytical techniques, and then probably worry about the more important test cases using some numerical techniques which we readily can use. So, that is how this week's lecture would shape up. So, till that time, goodbye and stay tuned. I will see you in the next lecture, lecture 3 of week 6. Thanks.